Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and this week I'm joined by Max.
Hi, I'm a first year math student at St Hugh's College, Oxford.
Cool. Max has brought some slides about Fourier Series. So we're going to talk about Fourier Series today. We're going to try and explain those. So we've got that coming up. I've got some admin to do at the front though. Sorry, Max, I will let you talk about Fourier Series. I've
Cool.
got some admin at the front, and also this is a good chance for people in chat to tell us whether they can hear us or not. We had a lot of tech issues last week; it was a bit rubbish. Alfie says hello, Max. Derishle's here,
Hi, Alfie.
having made a cup of tea. So if you want to join the live chat, if you're watching live, we're at slido.com/OOMC for the chat. It's nice to have the chat over there because you can have a username and you can let us know, I don't know, where you're watching from and where the tech's working. Hi to Ali and Harriet and Raphael and C. Thank you, people telling us that the sound is working. That's good to know so far. Hi to Tilly and an anonymous person who just says, "Hi, we can hear you," which, I set my expectations very low for my streaming ability. YouTube's just given me a warning message about audio bit rates, which is very scary. It's a possibility you can't hear me. Never mind. I'm going to keep going. What a day. Okay, coming up today, I've given you the title slide already, but coming up we've got sine and cosine stuff. Signs of things to come, I suppose. We've got those functions from school in a new and different context. We've got so much pi, loads of pi coming up, and if we get to it, a good fact about pi that we'll have as well. Hi to another Ali and Paula and Jonathan in the chat. Jonathan says it's their first time having just found out about the channel. Hi, nice to have you here. And applied maths, maybe, coming up today. Possibly my chance to talk about applied maths a little bit in this. There is no further reading in March. Sorry. That's me reading the slide because I've forgotten why I put this here. Oh yes, the maths website is going through some changes at the moment, which means that I can't post further reading during March. I'm going to write further reading notes. You can't see them, but I'm going to write further reading notes, and my hope is that maybe in April I'm allowed to put those onto the internet for you to see. It's also the reason why, if you follow our YouTube channel or if you're looking at the Maths Club website, we've scheduled quite a lot of live streams in advance, so I'm really sorry for spamming your YouTube feed with a month's worth of upcoming live stream notifications all at once, and that's partly because of our website changeover. By the end of March, we're going to have a shiny new website. Don't get too excited, but everything's going to be slightly formatted differently when this is all over, and further reading will appear at some point. Right, that's my apology to the huge numbers of people who go and look for the further reading. They're still up there for previous episodes on the Maths Club website if you want to read more about the topics we've discussed. And that'll be over there. Good, right, cool. Fourier Series. So, over to Max, I think. Do you want to say anything about Fourier Series before we dig into the content?
No, I think let's start with the stuff about sine and cosine, and then
Yeah, sure, okay.
Fourier series will appear.
Fourier Series will appear. Okay, I love it. So I thought start with cosine squared of x. I've written it out as cos of x squared. Sometimes people write as cos squared x, which is some function of x. And our challenge is to try and write that in a different form. There's a fact you learn in school at some point to write this in a different form. The different form helps us to sketch the graph. I think that's right. That's what we're talking about, isn't it?
Yeah, yeah.
How does it work? What are we doing?
So I mean, cos squared is a really awful function to deal with. It just doesn't make a lot of sense. But then in school, you learn that it's a half of the cosine of 2x plus 1. And that's much nicer. Yes.
Quite often it's nice to have it in this form, cos 2x plus 1. This is a good trick if you're trying to do some integration or differentiation. I mean, if you can integrate cos 2x or differentiate cos 2x, then this trick gives you a way to integrate cos squared x, or the square of cosine of x. Also, if you're trying to plot the graph, Um, this feels a little bit like an interview question or a graph sketching question, right? To try and graph the picture of cos x squared. Sometimes people are a little bit off put by the graph of cos x squared, the square of cosine of x. I'm trying to say it clearly because some people find this notation cos squared x really confusing, and it is confusing. It's inconsistent with some of the other notation we use in maths. Okay, we'll try and sketch the graph of this. Max, it's a slide on my computer, but do you want to help by telling me what to do?
Yes. So it's so with the whole point of like this identity is like cos squared of x. Trying to draw it seems misleading because it's like a squared, like the negatives go positive, and then in your mind you kind of imagine it being like bumpy at the y equals 0 line. It's like that graph there is cosine of x. So because it's squared, maybe you'd imagine it having these ugly bumps like that, but it doesn't, basically. Because it's half cosine of 2x plus 1, it's exactly like a normal cosine graph with a higher frequency, and then but instead of going between -1 and 1, it just goes between 0 and 1. So it looks like that.
Oh, I think I did okay. I think we're doing all right with the... Have I done that correctly? I think I have 0 in the right places. Yeah. So it's related to the other things, which means that, normally people draw it, if you just show them this, draw it by having these sharp cusps. But actually it's really nicely behaved. This is a really nice function. It's just like a cos graph that's been transformed by being squashed and then translated up and then halved, so squashed in the y direction as well. So it's a sort of squishy thing going on to transform cos to cos squared, which I guess from a distance you might not predict. Oh, by the way, because of the symmetries, this lets you work out if you need the integral of cos squared x from 0 all the way up to, let's say, 2 pi. This picture lets you work that out because cos has got some sort of nice symmetry. It's got some reflectional symmetries and some rotational stuff going on, which means that it all averages out. You can jigsaw puzzle the top bit into the bottom bit, which means the area above is the same as the area below between 0 and 2 pi. This is a good trick because it means that you've got this kind of jigsaw puzzle with this top bit. This top bit of jigsaw puzzle must be the same area as this kind of bottom bit of jigsaw puzzle. This bit underneath. So you can pull them apart to get the integral, which is what I want. You can pull them apart to get the integral, but if you stick them together, you get 2 copies to make this big rectangle of width 2 pi and height 1. So this integral must be exactly pi for exactly half the thing. Hi Jonathan, who I think is here for the first time, who's calling me out for saying squishy squashy. That's just how we roll on this live stream. Squashed because it's got to be squashed because good intuition for why it's squashed from Ali. It's got to be squashed because the squaring a thing gives you something between 0 and 1. Shout out to more people who have just arrived. Hi to Jerishle and SVE and Molly as well. Cool. Sorry, I got distracted by doing some integrals. What are we doing?
Good question.
Yeah.
So yeah, I mean, we've turned this sad function cos squared of x into this nicer function that's just a normal trigonometric wave, and then we can start thinking about, okay, so we can do that with cos squared of x. Are there any other functions we can do that with?
I think so. Are there any other functions we can do that with? I think I'm trying to remember in school if you can use. This is a bit of a tangent, sorry. I think in school you learn about cos. You can also work out these expressions for like cos 3x and cos 4x. I think I've seen those in like A-level questions to go and work out cos 3x using perhaps facts that you know about cos 2x and cos x. Maybe we could do some of that as well to split those up. So perhaps there's other functions that we could rearrange. So like cos 2x gives us a way to do cos squared. Maybe cos 3x tells us something about cos cubed, and so on. So there's maybe some other functions that we could play around with. But in fact, there's quite a big answer to this question, right? Of things that we can write in terms of sine and cosine. Maybe we should be clear about what that means. What does it mean to write something in terms of sine and cosine like this?
So I mean, with the cos squared x, we had that cos squared x is equal to half cos 2x plus 1. So I guess what else can we write in terms of sine and cosine x? Writing a function in terms of sine and cosine x means writing it as the sum of different cosines and sines with different frequencies.
Sure, okay, so we could have maybe
like that, yeah.
Things like this, and I guess there's these 1/2s in here, so we could have like some numbers at the front.
Yeah, well, they're all just constant numbers.
Yeah, okay, we could have some like constants. Yeah, people in chat are telling us about decomposing cosine things into sums over other cosine waves. So maybe something in the further reading coming in April might be an exercise to try that out for writing particular functions like that. Maybe we're kind of interested in things we can write in terms of lots of cosines, and maybe some sines as well. No reason why we couldn't use some sines as well, I guess. We could have some sine x and sine 2x and stuff like that. Sure, maybe that lets us write some big general class of functions. Do you want to hit them to the punchline of what we can do with this?
So what kind of functions can we write in terms of sine and cosines? Well, basically all of them. So any function that like repeats after a bit, which is called a periodic function, a function that repeats, we can write in terms of a sum of sine and cosines.
Yeah, so we can. This is just ridiculous, right? That we've checked cos squared, and now we're trying to claim that actually you could do a lot of different functions like this. Basically, all of the periodic functions with some mild caveats. People in chat are very excited. Because they've heard of Fourier transforms. I think it's people who missed the title slide who are excited that they might have identified that it's going to Fourier transforms. If you were here for the title slide, then perhaps that's not
Cheating.
so much of a cool shot. But here's the big sum. So we've got the expression written out using this big sum notation, where if you haven't seen it before, this big sigma just means we want to add up everything inside this expression for n is 1 and plus that expression when n is 2 plus the term when n is 3, like the thing that I just tried to write out with all the terms. So a1 cos 1x plus a2 cos 2x and also the sines, a3 cos 3x plus b3 sine 3x and keep going. We've got these constants an and bn, and this is called writing it in terms of a Fourier series. As I say, the title on the website as well. People who are looking at the website have also got clues as to what the content might be. And because of scheduling, you've got clues for the next 4 episodes as well, so you can look forward to that. S3ep8, right? Okay. Okay, so this is the idea. We're going to write something in terms of adding together cosine and sine waves. To try and give you an idea of a really one you might not guess that you could write in terms of sine and cosine waves. Max, you picked this function, and then you did some calculations, and then I built a visualizer for it. So we're going to try and visualize what this sum actually looks like in practice. Oh my word!
Cool. So I think the function he's talking about is f of x is equal to x between minus pi and pi, and then after that, it just repeats. So it's like the straight line between minus pi and pi, and then after that, on either side, it's just copies of itself, and then it's a periodic function because it repeats.
I'm trying to load my visualization. Oh, okay.
Yeah, that's much better than my fingers.
I'm trying. Some quick hot coding is going on. Yeah, okay, right, good. I've got the function.
There you go, yeah.
There, nice, right, okay. I hope that's turning up on the screen. It's a function that's equal to x between minus pi and pi. I'm saying it again, like, minus equal to x between minus pi and pi. It's to buy time. Equal to x between minus pi and pi, and it's periodic. It repeats every 2 pi. So the repeating bit is, I guess, a bit like sine. The next thing we draw is perhaps not that convincing, but if I do that,
so yeah, I mean, they don't look very much alike, like at all. But I mean, you can kind of see it. Like, you can see how like it doesn't get less bad as you go along. So like each wave is kind of like the same similarness to f of x equals x, and like it's kind of there. They have similar qualities. They're both, yeah, it's a push.
This is sort of a least squares thing. So what I've done is I've taken Max's function that's x between minus pi and pi. I mean, at least that's periodic, so I've tried to draw a sine wave on top of it, and there's sort of a least squares best fit going on, where I've tried to pick the best possible sine wave, which is not very good. No one should be very convinced by this picture comparing Max's function to just one sine wave. This is the sum when n equals 1, so just taking one term.
Yeah.
I'm mixing notations a little bit, sorry, I've realised. But the sum was for all n. Here I've only got one term.
Yeah,
can we
that's just one sine wave overlaid over the f of x.
Yeah. So that distance between graphs is in terms of the integral of the square of the differences. There are other ways to formalise the idea of difference between graphs. Good question. Can we try out hyperbolic functions? Yeah, you need periodic functions, so you need to make them periodic. This one was not periodic. Okay, right, sure. I'm stalling for time so that if this breaks, we've at least seen something. If you give me two, so if you give me two terms, I regret my notation, so that the counter is supposed to be, this is the sum of the first two terms. It's the original sine wave plus something like sine 2x on top of it. It's a bit better, right? I haven't made things worse. That was one. Then with two terms, I can do something like that. There's some.
So now instead of just having a sine x wave, we've got a sine x plus a sine 2x, each with different amplitudes. Yeah. And we add them together, and now we get this, which is a bit better.
Yeah, so I've maybe confused matters by saying least squares, which is a statistics thing. I'm behind the scenes. I'm in my code. It's picking up the right coefficients to use, the right constants, a_n's and b_n's in there. I'm going to put a third one on. So if I add another bit, I can choose my next one, which is constant times sine 3x. I can choose that one to just fix it a little bit, to do something like that. In fact, let's give it some more beans. It's still decreasing a bit over here, which is embarrassing. But if I give it some more beans, then maybe I can make it like that, and then that's not so bad. It's much better around here. So by 5 terms, it's now doing quite a bit better. It's still oscillating because I'm adding together sine waves that are really, really oscillatory. But hey, the oscillations are quite small. They're mostly cancelling out in the right way to give me the function. Yeah. So there's questions in chat. Sorry, to join chat in as well. Is there a specific way that we can combine the sine waves? There is a very specific way to combine the sine waves that we're going to show you what that is after I've messed around with the demo. There is a very particular rule for choosing the coefficients, those constants in front of the sine waves, to get it to add up properly. There's a request for putting my code in the further reading. My code is so messy. Right, I think they're not quite ready for lots of terms yet. Yeah, so to be more precise, is my code brute force finding functions that reduce the mean squared error? No, it's using some actual maths that's equivalent to that. I've been slightly disingenuous. I mean, it is true, it is minimising least squares error, but that's perhaps not exactly what my code's doing. Anyway, let's look at adding on a few more sine waves. If I do that, then now look at this. So near this bit, oh, I'm doing great now. I've got, let's go to 20 terms. So if my computer does that, Max, you're doing a course on this at the moment, right?
Yeah.
You're a first year student doing Fourier Series
Yes.
as an Oxford course. Could you describe what's going on in this picture?
Yeah, so yeah, as like n grows, as you have more and more sine waves of different frequencies like piled on top of each other, as you can kind of see, the approximation gets better and better and better. But except for no matter how big it gets, I think what James is hinting at is that like at the edges where it jumps, it doesn't really make sense. So like no matter how many sines and cosines wave you have, at the discontinuities, it doesn't make sense for the sine and cosines to have a value. So it kind of goes a bit. It doesn't converge at those points, no matter how many you've got.
Yeah, so my function's kind of in trouble. That adding together all of these sine waves is quite good, but it's always going to be a continuous function when I've got
Yeah.
finitely many of them. I'm always going to get some nice smooth function. It's not going to be able to do this jump. It's one of the reasons that we said basically any periodic function, because you can have these problems where as I go up to stupid numbers of n, I think if I click here it adds 10. I think if I click here it adds 10. Oh, there we go. As I go up to stupid high numbers for n, it does really well for Max's function across most of this region, and then it's really highly oscillatory and it's really having a bad day with the bit where Max's function was had a big jump in it. We call that discontinuous. Continuous, like a smoothly changing thing, and discontinuous with this big jump. It's really having a bad day with that, even if I go up to sort of 100 terms. Yeah, so this has got a name. This is called Gibbs phenomena. It's the kind of mixed results, I suppose. What this picture's showing us is that by adding together lots of sine and cosine waves, we can do a really good job of matching this function, but they're not very well if your function underneath.
So like as you increase the number, like the width of the bad bit at the end gets smaller and smaller, but like the size of the error at the very end doesn't change. So like as you can see, as n increases, more of the graph looks good, but the bits that don't look good don't get any better. Which you can kind of see, like, no matter how many sines you've got, it's always gonna be continuous, and mapping and fixing that to a discontinuous function just doesn't work.
Yeah, so question in chat, as n turns to infinity, as n gets really big, the gradient of this function matches up with the gradient of Max's original function, which is 1, over here and over here. But the gradient of the function is really bad around here for any particular n, where around here the problem region gets smaller in width, but it stays the same height. So the derivatives get really, really bad around here. This model does a bad job of describing the derivatives, especially nearby the edges, the gradient of the curve. It's sort of nothing like that around the sharp corners. It's really picked out a feature of our original function that perhaps we didn't talk about it. I guess you don't talk about this in school, but a feature of the original function is that this function is nice and continuous over here, but then it's discontinuous. It's got this big jump, which matters. Okay, that was the visualizer, showing that we can do quite a good job of adding up all these coefficients. Yeah, the gradient approaches infinity and minus infinity in the edge, and the very wiggly bits. It's pretty bad. SV would like to do this all with complex numbers. You can, if you like, throw in some. You can replace the cosines and sines with e to the in thetas. Nobody's stopping you. You can do what you like. Go for it. De Moivre away. Same story whenever you see a cosine or a sine. Okay, I'm going very slowly. But that's because I wanted to show the pictures before we tried to work out the coefficients. I said something about least squares and minimising error, but there's a much better way to work out what these coefficients are. It turns out to be the same thing as doing some statistics least squares thing. There's a really good way of working it out. We got this idea of how we would like to write our function. I think we're now going to show them some useful integrals. I think. Ah, yes. Okay. What do we want to say about these?
I mean, it's really weird if you think about it. So what it's saying, basically, is that the integral between minus pi and pi of, so the top one, the integral between minus pi and pi of the product of two different cosine waves with not necessarily the same frequency. If they are the same frequency, then no matter what the frequency is, the integral is equal to pi. And if they're different, then it's 0. And that's kind of really weird.
Yeah, so this integral on the left, cos mx cos nx, is, I guess, the product multiplied together, two different cosine waves. And then if it's the same, then it's a bit like my cos squared integral from before, the one that averaged out to be pi overall when you integrate across that range. If m and n are the same number. But if they're different numbers, then it sort of cancels out. The cosine waves are positive or negative in different places.
Yeah.
And it's sort of destructive interference, I think.
Yeah, but it's so weird because it doesn't matter how different they are. It could be frequencies of 100 and 101. So looking at those graphs, they look very, very similar.
Right.
But it would still completely annihilate.
Yeah, it's not just an odd even function thing from suggestion in chat, because the top thing is even for any value of m and any value of n is an even function. There really is a good reason why that's 0. You can work this out using A-level maths, I think, depending on how many facts you know about things like cos of... Somebody put one of these in chat earlier. If you know things about cos of A plus B and things about cos of A minus B, possibly also sine of A plus or minus B, then you can go to town and work these out. If you like complex numbers, then you can think of this as... Oh goodness, can you do something with De Moivre? I bet you can. I started saying that because I assumed it would turn out to be true.
In fact, I had a go at that in A-levels, and I think what actually happened was I used the e to the I m and e to the I n, and then you ended up with something that was 0 divided by 0 divided by m minus n, and if they were different, that means you'd get 0, but if they were the same, you'd end up with 0 divided by 0, and the limit tended to pi. That was what I got, which I thought was really cool because it kind of sees where it comes from, but I don't really remember the details. But
so this, I can sort of see the second one of forcing to get complex numbers in. The second one tells us something about the integral from minus pi to pi, but this time we'll take a cosine and a sine. That one's always 0, no weird business. I think this one, if you love De Moivre's theorem, is the imaginary part of the integral from minus pi to pi of e to the I mx, e to the I nx, I think. Is that true? Maybe over 2? Oh, they'll be cross in the comments if I can't get this right. I think it's this, which then is the integral of an exponential. Is your thing about m plus or minus n? Or yeah, I've become worried about my minus signs. Maybe this is just always 0. Maybe that's not true. Cool. Or yeah, or integration by parts if you're very brave and like doing integration by parts. Cool. And we've also got something about sines as well. Sines are just like cosines that have been shifted a bit, so maybe this is not surprising once you've seen the first one, that sines satisfy this thing, that you integrate the same one against itself, you get pi, you integrate two different sine waves, you get 0. It really is discrete. We're only talking about whole numbers today, but for m and n. But it really is true that if they're different at all, then this integral detects that. And if they're the same, then it picks it up. What do these relations have to do with Euler's theorem? Nothing yet, I think. Although maybe I've confused matters by putting de Moivre's thing on here. If you haven't seen de Moivre before, then you're in for a good fun bit of maths. I think I've also messed it up. We should change the slide. This gives us a great way to work out those Fourier coefficients, and those coefficients in the sum, using all of these integrals. So we're not going to prove these integrals. We reckon you can with integration by parts, or facts about cosine and sine that you know from school, or de Moivre if you're feeling really flash. Instead, I'm just going to use them to do a thing.
Yeah.
Okay.
But like, I'm sure you could find them online as well.
Yeah. Here are some facts. Yeah, okay, so what we've got is we've got our function which we've decided to try and write in terms of this big sum, in terms of some cosine waves and some sine waves. Okay, and we've just seen that integrating different cosine waves or integrating cos and sine against each other gives you 0. That means there's a really good idea of something we can do to f of x. Do you want to say what it is, Max?
Yeah, so you multiply both sides of the equation by cosine of mx, not nx, but mx. And then you get a0 over 2 cosine of mx. And it's a sum, so we can just multiply every term in it by cosine of mx. So it's an cosine mx, cosine mx. And the same with bn's. And then we integrate both sides between minus pi and pi.
Okay. So you want to multiply both sides by cos mx and then integrate from minus pi to pi.
Yeah.
I think I can fit that in. Okay. dx. And then also a massive, this is going to scare people, isn't it? It's a big integral of a sum. If you just met sum just now, I'm really sorry for all this notation. But hey, got an integral sum of loads of cosine things. Great news if you're terrified of this. Most of it's about to disappear. Most of it's about to disappear because if m and n are different numbers, then this thing here is 0. So when I'm thinking about this sum over all the different values of n, most of the time I get 0. So it doesn't matter what A1 is or A2 or A3 or something, it doesn't matter what they are until I get up to when n is equal to m. Yeah.
Because it's a sum, we can integrate each term separately.
Yeah.
And pull out the constant in front of it, yeah.
We could do each integral one at a time for a particular value of m. If we do that, then most of the integrals turn out to be 0 because of this relationship about integrating different cosine things against each other. We can do that. What that means is that this bit here, so I'm going to write my equals sign in, I'm going to write some stuff. This bit here, all of this sum with infinitely many terms in, almost all of them go to 0. They just integrate to 0, so it just gives me am times, and then if I'm using the fact from before, times pi. And that's it. The fact about these cosine waves when you integrate two of them together. That fact involved so many, like, it involved any values of n and m, so it's sort of really good like this. What else can we say?
So, and then with the bn, so we've got all of the cosine of mx and sine of nx, and then I mean we're summing over n, but no matter what n is, that's still always going to be 0. So then we don't have any of those at all, not even bn. So that's just 0.
Yeah, cool. I think.
How can we be sure we can swap the integral and sum? That's a great question that we're going to ignore, basically.
I think, Adam, I think you'll really like university mathematics. Please come and study maths at university. How do I know it tends to 0? Well, I guess nothing's really tending to 0. I'm just integrating it and getting the number 0 for each of the terms.
So from the previous slide, we had the integral of cosine of mx times the sine of nx is equal to 0. And we're integrating that infinite sum, so we can integrate each term one at a time. So yeah,
we can integrate each term one at a time, and then most of them are 0, which should be quite relaxing for people who are worried about infinite sums and series. Unfortunately, there's something we have to worry about, and this is actual maths underneath the bonnet. I'm really pleased that somebody asked. I thought I got away with it. Anyway, so this pulls out just one number. This one, I guess, we're doing it if m is bigger than 0. Then this thing is also 0, which just gives me this lovely relationship. That if you integrate with this cos mx, like Max told me to, then you just get am, the thing I want, multiplied by pi.
So it's am pi rather than am pi because n is like the dummy variable in the summation. So that means that like the summation is like exactly it's adding up each of those. But the only time that it isn't 0 is when n is equal to n, but because n is the dummy variable. So when we reach the pink circled item in the summation, then that's the only time that the integral is not 0, and then it's equal to pi. And then from the an coefficient, in that case, because like n is changing for this case where it is pi, n is equal to m.
So brilliant. Okay. Also, so there's a question which is good: is can we actually do the integral on the left? And I suppose if we can't, then it's hopeless. We can't calculate the Fourier coefficient like this. But if we can, I think we have calculated the Fourier coefficient. Now, the question about whether or not I can actually do the integral of the function you give me with cosine mx. Maybe I give it to my computer and I work out that coefficient like that. But if I do, this becomes quite a nice formula for what am is. So that if I want the nth term, that's hard to say, the nth term in this series, I just need to integrate my function multiplied by cos mx and then divide by pi. And for a nice function, I can actually just do that integral, which is pretty good. Isn't not refraining from failing to avoid being 0. Yes. Good. There's another expression for the bn's. Let's get a suggestion in chat. Interactivity, hooray. Suggestion in chat. What do you think happens for the bn's if I want this b coefficient over here? How do I get it? And maybe what does it turn out to be?
Yeah. It's very similar, but...
and yes, if you're periodic on a different interval, then I would do some shifts and transforms to make it periodic on the interval minus pi up to pi.
Yeah.
Which is not too bad. And then undo the shifts afterwards and say, oh, look at my function. Suggestions in chat. I'm going to give people a minute to join in as well. Chat lags a little bit, so that also depending on how fast YouTube is getting data to you, getting people to join in at some point. And there's maybe a suggestion we do the same thing. The only difference between these is that this one's got a cos in it, this one's got a sine in it. And that's good because the only difference to our method is that maybe we should try multiplying the expression by sine instead of cosine. Yeah, multiply by sine mx. Cool.
And that works because like where we had this am pi that came from the integral of cos mx, but if we multiplied by sine, then we'd have bm next to the integral of sine nx, and that's the same pi.
Good. Yeah, cool. So there's this equivalent expression, I guess. There's one slight extra thing to say, minor thing to say, which is that somewhere in here we said if m is bigger than 0. If m is equal to 0, I might get this a0 thing out here. It turns out that a0 is equal to 1 over pi. Oh, excuse me. On autopilot. Minus pi to pi. I think that's right, isn't it?
Yeah.
Which is also right. What you would get if you put 0 into the previous formula. So it's sort of a special case because the reasoning is slightly different on the way through. The reasoning becomes all about this integral and not about the other integrals if you're looking for a0s. Okay.
Yeah, but so it's a0 over 2. It's still just a constant, but it's only got that over 2 because to make the integral expression for it look nicer. Otherwise, if it was just a0 plus that infinite sum, then you just define a0 to be 1 over 2 pi. That's all the reason the plus 2 is there. It just makes it look nicer.
It's tough. It always
but it's still just a constant.
I find that it always confuses students learning about it. That hey, here's this weird expression. It's gone over 2, which seems completely unnecessary because it's just a constant that you're adding onto your expression. But the only reason there's a 2 here is not actually important. It's just a 2 here, so that I don't have to write a 2 here. And because I don't have to write a 2 here, it's easier to remember because now it's the same with m equals 0, provided I can remember there's a 2 up here. Right. Okay. I think we should hit them with some sort of example. We've got 4:45, so we should do the example because we advertised loads of pi.
Yes.
We've only had some pi so far, so I think I've got appetite for more pi. Right, cool. Okay, pi. I think I know where this is going, but it's another one of your functions that you picked. So I think we're going to do this for, a different function. Do you want to explain what this one is?
Cool. So kind of like when we had f of x is equal to x, and then repeating every pi. Now we've got f of x equals x squared, repeating every pi. And like, just a little note is with the equals x, we had that Gibbs phenomenon at the edges because it was discontinuous. Because x squared because it's even, so because it's like symmetrical in the y-axis, then like at the points x is pi, x is 2 pi, x is minus pi, whatever, it matches up. I think that's easier to draw, so it's not discontinuous anywhere.
I have a picture for this one too, which I'm desperately trying to load. That has not worked in the way I thought it would. Oh, I know what I'm doing. It doesn't look like I know what I'm doing, but I do know what I'm doing. Okay, that one. Yeah, cool. Okay. Yeah, cool. Right, good.
There he is. Yeah.
There he is. Okay, so totally professional live stream. Nothing ever goes wrong or fails to happen. This function is x squared between minus pi and pi, and then you've made it periodic. And somehow, because of, I guess, even odd function stuff, that's the same strategy you had for making the function x periodic. But this one, because I guess it's the same value on the left and right, you make it periodic and you get this thing that just bounces up and down, like that. Yeah, so this function is spiky. It's continuous. Oh, I didn't realise we were going to be doing this much first year analysis of functions. This function is continuous. You can draw it with a pencil without taking your pencil off the paper. No jumps. But its derivative, its gradient, is not continuous. It's not very nice around these top bits. That turns out to be not so bad. That's all right. Just give you a visualization of what this looks like. Oh no, let's do it in the right order. So we can go and calculate. We've got some formulas now to work out what these things are. Wasn't really sure how much of this I was going to do, but we've got some formulas, so hey, we could just sort of go for it, right? This says something like, oh goodness, now I'm integrating live on stream. Here we go. You're going to tell me if I go wrong, right?
Yep. I'm going to load up the...
You've got notes.
Yes.
This is the for the people watching at home. These are Max's slides, Max's functions, but the slides are on my computer, so I'm writing and Max has got all the notes. I think I've done all right so far. Okay, so I've got a0 is I think 2 pi cubed over 3, which it means that my Fourier series expression starts with, remembering the 1 over 2, starts with pi cubed over 3 plus some big sum. Okay, so it's first number in.
Because it's a0 over 2, which is why the 2 disappeared.
Oh, is there a 1 over pi? Ah, there's a 1 over pi. Someone in chat's told me there's 1 over pi. Who's this? Credit where credit's due. An anonymous person has told me there's a 1 over pi.
Oh yeah, it is squared. I missed it too.
Yeah. You were supposed to be watching.
Sorry guys. Oops. One job.
Thanks, chat. The good news is all of chat are watching us as well, and will catch us up for missing factors of the pi. Okay, pi squared over 3. And I can put that onto the picture. Oh no, I can't. There isn't any slider. Oh. Yes, slider. Right. Okay, pi squared over 3, which is frankly embarrassing, right?
Yeah.
A terrible representation of the function. It's captured none of the information about what this thing is. Really terrible. But we can do better. So if I try and work out I'm going to go for 8m. Do I want 8m? Yeah. 1 over pi. I haven't decided if I'm brave enough to do this one live. What's your recommendation? It does intersect it. It's sort of an average value in some sense, but not in the normal, not in the normal sense of being an average value. It's an average value in quite a strange sense. Oh, shall I try and do this one?
Oh, that's brave. Go for it. Yeah.
Okay. Can you talk over it? If I spend 2 minutes doing it, can you talk over it?
Yeah. Cool. Okay.
Deal. Right, okay. Let's go.
So, integration by parts, I'm hoping is what he's going to do. So, like, letting u equal x squared and then dv of dx equal cosine of mx, then it's so then like u prime is equal to 2x and v is equal to 1 over m sine mx. So then by parts we get this. So x squared 1 over m sine mx is 0 at both pi and minus pi because m is an integer. So sine of any integer times pi or minus pi is always 0. So that just disappears, which is great. And then this integral we're left with here, x sine mx, parts again, letting u be x and dv of dx equal to sine mx.
There's some minor signs for me to worry about this time round. Here we go.
Yeah.
Okay, so square brackets. I've got my u is x and my dv is that, so I want a 1 over m and a cos mx and a minus sign. Pi and minus pi. How's chat doing? Are we on so far? Someone's going on Wolfram Alpha. So I'm also going to know if I'm wrong or right at the end. Brilliant. What am I doing here? This is minus the integral from minus pi to pi. I've ignored this 2 over n pi stuff over here, so that I can focus on getting this bit right, which is this. Derivative of u is 1. Integrate that, and I get some trig function that I don't really care about, because the integral of cosine from minus pi to pi is 0, I think. Whoa. Yeah. Pretty sure that's 0. Cool. Okay, so I'm going to plug in pi and minus pi over here.
Yeah. So
I think I get.
So yeah, cos of m. So yeah, we have cos of m pi, and then plus
the negative of that.
So,
Bring in minus pi, flips both of them, get it back again. Oh.
Because cosine's even, x is odd, then like when you put in minus pi, you get minus what you get when you put in pi. So when you subtract that, you get twice the same thing evaluated at pi.
Phew. Okay, I think the minus cancel, the 2's cancel, and I get 4 over m squared. And I know that cos m pi is equal to minus 1 to the m, I think.
Yes. Yeah.
Oh.
And that's right.
That was 3 minutes. I said 2 and it was 3. Oh, right, okay. I think we got there. I've got some expression for am. This is what my code's actually doing, by the way. I work out the coefficients and then feed them into my computer, and it will just add these up. All it needs to do now is I've got some nice formula. Integration by parts. Do I regret doing it? No, this was good A-level revision for everybody. A-level or equivalent. Integration by parts. You should be able to do this at home. Cool. Probably better than me at doing it at home. Right, okay. So we've got some formula for the AMs. This is really good news, because now I can get my computer to take those and to add them on. So the first one's not great, but then as we add more of the terms in, with this 4 over m squared minus 1 to the m thing, it gets better and better and better. And I think, as Max said, because this one's continuous,
there's no Gibbs phenomenon.
Yeah, it actually does really well. And actually does, most of this slide is pointless. You can't see the difference at all. It's just great. It converges really quickly, because these coefficients like decay like 1 over m squared, which is really fast. So the later ones don't really matter at all. It's just the first 10 or so that matter. Cool. Good. Okay. So we've got some nice expression, which gives us. I'm going to put it on the board because it looks amazing.
Just worth pointing out that bn was 0 because it would have been the integral between minus pi and pi of x squared sine mx between minus pi and pi, and you can do the same part stuff as before and show that it's 0, or if you're happy with the idea of like odd and even functions, x squared sine mx is an odd function. So an odd function integrated like symmetrically over the y-axis would give you 0.
If people aren't happy with odd and even function, this is good because they've seen basically some sort of wizard method to avoid doing that integral and just declare it to be 0, and that might be the prompt you need to go and learn about odd and even functions.
They're great.
Observations, yeah, it's really weird for small values of number of terms. It's really odd. I spotted this one as well. It's really flat around here when I've got 3 terms. I can't really explain that. I think it's just not very good. I mean, it's got 0 derivative around there, and it's adding together lots of cosine waves that all
lots of cosines, yeah.
All have 0 derivative, but it works itself out after a while. So, yeah, just one of those things. I think. Look at this fact. This fact's amazing. Yeah, sorry. So we got a chat suggestion as well. What happened to the BMs? I got too excited.
Yeah.
I got the integration by parts and then moved on.
The BMs are all 0.
They're all 0. There we go. Thanks.
Which is easy. It's great.
It's easy and great. It gives us this fantastic fact.
Yeah, I mean, you can try like plotting that on Desmos or whatever, and like I promise, this is the pi squared over 3 plus that like infinite something is what James was just graphing there. Like, Cool. So
Good point. I
now
could
we've
have
got
done that in Desmos.
yeah.
I made a thing with a slider myself. I could have put it in Desmos. Homework, if you like. Plunk this into Desmos and play around with it and try and see what that looks like. I like it because in school you learn how to write cosine in terms of different powers of x squared. You learn some Taylor series or something for writing cosine in terms of x squared. Whereas at university for Fourier series we teach you how to write x squared in terms of cosines. Other way round. This is true. Yeah, that's a good caveat for x between minus pi and pi, and after that, not so true.
Because we defined f of x to not be x squared, but to be x squared and then x squared repeating itself. So yeah, it's only x squared between minus pi and pi.
Sorry, yeah.
But if we look at x as pi, then it does work. Because like on the graphs you saw that at x is pi, this series was the same as the black line. So it's like it's an inclusive minus pi that's equal to x, that's no equal to pi.
I should really put this on the board.
Yeah, it's just kind of the whole next point relies on letting x equal pi. So if you set x equal to pi in this like equation we've got above, then we get pi squared is equal to pi squared over 3 plus 4 times the infinite sum of minus 1 to the n over n squared times the cosine of n pi. And now the cosine of n pi, this is mentioned earlier, but the cosine of n pi is minus 1 to the power of n. So that means that like in this infinite sum, we've got minus 1 to the power of n times minus 1 to the power of n. And no matter what n is, that's going to just be 1.
Cool. So we can rearrange this a little bit, right? I think we can rearrange this to get 2 pi squared over 3 over here. And that stuff inside simplifies quite a lot. And then we can divide by the 4.
Dun, dun, dun.
That's amazing.
That's so cool. Yeah, I mean, it seems so weird. Like, there's no circles involved. I mean, the infinite sum of the reciprocal of the squared shouldn't have anything to do with pi. It just shouldn't.
Yeah, this says, to be really clear, forget all the Fourier series stuff. This final result down the end says that 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, the square numbers, 1 over 25, 1 over 36, and so on, forever, is exactly equal to pi squared over 6.
Which is just messed up.
It's
completely.
So that's a sort of great fact that you get for free for having done the Fourier series. You need to know that stuff converges along the way. So there is some sort of hardcore mathematics hiding behind the scenes to make sure this actually works when x is equal to pi, not just up to, but not including pi. Make sure it's okay there. But once you've done that maths, you've got this really nice result for free. You can pick other functions, like I think x to the 4, I think gives you an expression for the sum of the reciprocals of the squares of squares is pi to the 4 over 90, and I think you can get that from thinking about x to the 4 with a Fourier series. It's a really nice result. Cool, I don't think we've got any time for applied maths. Cool. Anything else to say about Fourier series before I do some more admin?
No, they're great. But yeah.
They are really good. They are also useful for applied maths, of doing, being able to write a complicated function. X squared is quite nice, but being able to write a complicated function in terms of nice, simple periodic cosine waves, it's pretty good if you want to analyse that function. Okay. It lets you calculate some values of zeta x. Does it generalise? Not very well. Okay, cool. Good fact. If you would like to see more sort of maths talks, I've now got an actual event to advertise. I mentioned it last week, but not very convincingly. We're doing our open days in person in Oxford in April, and it'd be great to see you there if you can make it along. We're going to do some talks about maths courses at Oxford, talks about maths as well. We love putting a lot of maths into our open days, and it's hosted in the maths building where the lectures are. So if you want to see the building, see a bit of Oxford, see some maths, this is us. We're open on 23rd of April and 30th of April. There's a timetable and you need to book onto the event so that we know who's coming, so that we don't have too many people in the building, I guess. You need to book onto that at the website link, which I've put on the screen, and you can come along. Bye if you're off. So question about offer holders in chat. Hey, let's just talk directly to one person. If you're an offer holder, I think you should get in touch with your college. I think they will be more than happy to show you around. I encourage you to get in touch with your college. Some of them are organising offer holder days. But I think all of them should be happy if you get in touch to say, come and visit Oxford, come and see things. If they say no, then sure, book onto my event. I would love to see you. Right, cool. Okay. Yeah, so question about the 2nd April 30th. Yeah, on the open days one, the second one is a bit longer. Each open day has got this staggered timetable. One of them starts at 10 and one of them starts at 11. And I get all of the speakers on the open day. Max, did you go to any open days?
Yes, last year.
Okay, so...
But that was online.
Oh, it was online, right.
Yeah.
Okay. What we do for the in-person ones is we run all of the talks in person, but we do 2 separate schedules, and every speaker does their talk twice. So if you're there, you don't notice, but everything happens twice. Once in one room and once in a different room, which is quite weird for the speakers to do the same thing to 2 isomorphic events in the same building. That's how we get everyone through. So one of them starts at 10 and one of them starts at 11. They've got overall the same content, except one of them on the 30th. Oh gosh, let's get the dates right. One of them on the 23rd. One of them on the 23rd involves some more computer science talks and has a slightly different structure. But if you're interested in maths talks and things like that, then I will see you around in Oxford or on other events. God, it's such a long-winded question to this thing in chat. Look at this thing. This is the timetabling for this event is very complicated. There's a very specific question in chat that I've done my best. Right, okay. Admin aside, thank you very much for coming on the live stream, Max. Thank you for telling us about Fourier Series. Thank you everyone for watching, and we will see you next week for another episode of the Oxford Online Maths Club. Have a nice week, everyone. Bye.
Bye.